Okay, welcome to Unit 1 on DSP, General Techniques, and Note Set 6 in that unit. This is note set in my Digital Audio Signal Processing course, and this is our second note set on sampling rate conversion. And in this one, we're going to talk about multi-stage approaches. Again, like in the previous note set, we're only going to scratch the surface on this. There's a lot more detail, some of which is covered in this chapter in Peratt's DSP book, but there are entire books on multi-rate signal processing. So if you really want to get into this stuff, you should dive into one of those. And as I said, the reason we're covering this multi-rate stuff is that there's some places in digital audio processing where we're going to need to change sampling rate. Take it up, do something, bring it back down, things like that. Or we've got audio digitized at one sampling rate and we want to put it onto a system that uses a different sampling rate, things like that. And at the end of the course, we'll look at some details of ADCs and DACs, and there are some tricks you can do in there if you can upsample and downsample. So that's why we're talking about it. So why are we talking about multi-stage schemes? We talked about last time how we could just, in one step, upsample by a factor of M, or upsample by a factor of L, or downsample by a factor of M, each of those factors being an integer. And we also alluded to being able to do any rational number factor. So we could put L over M with any choice of integer L and integer M and get a rational factor to change the sampling rate. That would require essentially two stages, as we'll see. One for interpolation and one for decimation. But here we're going to start off just looking at decimation, and we're going to say, why would we not do this in just one step? So one filter, as we said, kind of like an anti-aliasing filter out front, a discrete time anti-aliasing filter out front, and then throw away samples. In effect, we talked about last time how you really shouldn't compute the ones that you're going to throw away. Just skip over those in your filtering stage. But it turns out that when M is large, so when we're trying to decimate by a large amount, and there are times in audio where we want to bring something down from a very high sampling rate. We'll look at some sigma delta A to D converters at the end of the course, where we'll see that our samples are taken at a very high rate, and then we need to bring them down to a more reasonable audio sampling rate. So we might end up with a very large M to do that. And I say here typically greater than 10, but that's just a rough guess. You'd really have to do the analysis using the ideas that we talk about here to try to nail down whether it's advantageous to do it for your particular M value. But when M is large enough, just doing it in a single stage, a single step, requires more computation than if you try to do it in multiple stages. And that's what we're going to see here. We'll go through some general stuff first, and then we'll illustrate this with an example. So why does this happen? Here's the real culprit here. Remember, if we're going to decimate by a factor of M, we need to start with an mth band signal. And that's what the filter at the front end does. And so we run it through a filter that has a cutoff frequency that is close to this stop band. So there's the stop band. That's going to ensure that we end up with effectively an mth band signal. And then the pass band is going to be somewhat close to that because we don't want the passband to be way down below, that would be saying that we're limited as to how far down we can bring our sampling rate. So typically the passband edge is pretty close to what our stopband edge is, so that we're not just sampling a section of spectrum that we don't really need. So that's the culprit, is that when we have a large M, it leads to the fact that we end up needing a filter with a fairly narrow transition band. So remember, transition band is the band between where the passband ends and the stop band starts. So, I'm defining that for a low pass filter as we're talking about here. And it turns out that the narrower that transition band is, the longer your FIR filter needs to be. Now you might say, why not use an IIR filter? And you can, but most of the theory and practice for this multi-rate stuff is developed nicely for FIR filters. And they're the easiest to design to very stringent specs, but they end up being long filters. That means that the impulse response is long, or equivalently, the number of coefficients in the FIR filter is long, and that increases the number of computations. So we have to do, for each output, we have to do a multiply for each coefficient in the filter. So that means that for each output, we'll have to do a large number of multiplies, and that number goes up as the length of the filter goes up. So that means that this is inefficient if we try to do it for a large M. So here's the solution. We're going to consider the case where M is not a prime number, but in fact can be factored into some number of factors that are integers. And it could just be a factor of 2, or 2 factors rather. It could be 3, could be whatever. So I've indicated that as P. And each of those M's does not have to be prime. We could leave some of those individual M's further factorable, but we should consider all of our options and work it all out. And I'll show you, I'll allude to a MATLAB command later that will do that for you. But danger using MATLAB commands that you don't really understand what they're doing. So that's what we're trying to do here. Get you to the point where you understand the ins and outs of this, so that when you use the MATLAB command, you understand what's going on under the hood to some degree. So we've got a signal x of n that is at some higher sampling rate, and we'd like to decimate it by a factor of m, so that we get y of n at this new sampling rate that is a rate of 1/mth of what it was at the beginning. And now we're doing it in p stages. Since we can factor m into p integers, we can now do a rate change for each one of those integers. So at this point here, we've brought the rate down by a factor of m1, and then here we've brought that down further. So at this point, we've brought it down by a factor of m1 times m2, all the way out to the end. We see that now we've accomplished our goal. Now here's the trick. We put a filter in between each of those decimations. So that filter is designed just to make sure that we don't get aliasing from this stage. And then this one is designed accordingly as well. And that's the trick. So let's see how this approach can lead to a more efficient way to do this. So far, we've just outlined that we can do it this way. We haven't really said yet that it actually helps us. So let's take a look and look at what our strategy is here. So the idea here, as I just alluded to, is that we can design this H1 of Z. Its design is going to be more relaxed from a single stage design, because the stop band for that only needs to be pi over m1. not pi over m. But the passband is going to stay the same. Every one of these filters in that cascade has got to have the same passband because that's the section, or at least the same relative passband. You'll see what I mean. Remember that things, things move around once we start changing rates, but effectively, as far as the equivalent hertz frequency goes, the passband has to stay where you want your ultimate signal to end up. But what's important is in that first stage that stop band is going to be farther out than we would have in a single stage. So that's what I'm saying here. This helps because the stop band is further out than we would have in the single stage. But it's even better than that. We can actually get more aggressive in our design than one might think. So what we can do is, instead of saying this, which is the obvious choice, we can actually let theta S be a little bit bigger than that. So we're allowing some aliasing to happen, but not so much that it won't get cleaned up in the subsequent stages. So that's the real trick here. So there's two things going on. One is this just naturally helps, that we have to have that. And then we can, if we're clever, we can push the stop band of the first stage farther out. And then we can do that same thing for the second stage to the third stage, and so on and so on. So I'll only illustrate this with a two-stage filter, and then, or a two-stage approach, and then I'll show you how MATLAB has a command that would allow you to, that essentially would do this for you for multiple stages. So that's the key. Let some aliasing happen, but clean it up in the next stage, or whatever stages come after that. So because of that, this is even better. It's pushing our stop band farther out. And remember, relative to the pass band, the pass band is staying the same. So that means we have made an even wider transition band, which means a shorter filter, which means more efficiency in our FIR. We're going to see soon a relationship that tells us how the transition bandwidth relates to the filter length. So we'll see that in the example. But for right now, that may be a characteristic that you learned about in a signals and systems class or a DSP class. So let's see how this works for just a two-stage case. We'll go through some general results for this two-stage case, and then we'll do a two-stage example to see how it really works and see what the improvements are. So let's say that we've got some signal x of n, and it has spectral content that we care about only up to some frequency theta sub p. Now, remember, that's really going to map back from the continuous time frequency. So suppose we have some f sub p. So for audio, maybe that's 20 kilohertz or maybe 18 kilohertz, something like that. So we have an audio signal that we care about things up to that highest audio frequency. I say 18 because that's the number that I use in an example later, just to make some numbers work nicely. But for us, it might be 20 kilohertz. And then whatever our original sampling rate is, that's what would map that to that theta sub p. Okay, so that's the idea. But we've chosen our sampling rate so fast that this theta sub p is quite far below our the value of pi over m. That means we can decimate by a factor of m. Now, again, you might say, why would we sample it faster? Well, we might have been forced to do that for other reasons, or to achieve other gains. And we'll see that throughout the course. So for right now, just accept the fact that we have oversampled this signal by a factor of m, and we'd like to bring it back down to a 1/mth of that sampling rate. And furthermore, we're going to say that this m here can be factored into two integers. I don't state that m1 and m2 are integers, but they need to be for what we're talking about here. So let's look at the single stage method. We just take m, we design a filter with a transfer function such that the signal here will have a stop band at pi over m. And then we do our decimation all in one stage, filter and decimate. And again, remember, as we said before, we would only compute the outputs of that filter that we're actually going to keep. So that's the efficient way to do that. And as I alluded to, there are things called polyphase structures that allow you to do that. But that's aside from what we're talking about here. So here's a picture. Our theta sub p is somewhere to the left of pi over m. This is our specified stop band that we need to make an mth band signal, at least a effectively mth band signal. And I'm showing that as a fairly narrow transition band. So sharp transition means a long filter. We'll see the formula that allows us to do that. Okay, that sets the stage for the, pun intended, I guess, for the for the one stage methods. Now let's look at the two stage method. So we've got a filter followed by M1, a second filter followed by decimation by M2. So let's go through and think about what these filters do. So let's look right here after the first filter, but before we downsample. So let's just state that this is what we need here. You'll see that this is bigger than that pi over m1. So you'll see that this choice here will allow aliasing to happen. Now at this point you can't see why I picked that, but you'll see how it works, and then you'll say that, well, that's the formula that I need. And we could work through this to show that that is true, but and then write it down, but I'm going to do it the other way. Write it down and then show you that it works. So notice, as I said before, the pass band in this first stage has to be the same as the pass band in the single stage. So again, remember, this would come from some f sub p, like I said, 18 kilohertz, 20 kilohertz, whatever it is, mapped to this number based upon the original sampling rate. Okay, so same pass band as the single stage. But now this is much farther out. Okay, if you look carefully at this, this is much larger than pi over m, right? Well, how much larger? Well, it's 2m2 minus 1 larger than pi over m. So, m2 is an integer. It would make no sense to make m2 equal to 1. You wouldn't be doing anything. So m2 is at least 2. So this is at least 3 times as big as what we had before, but could be quite a bit bigger depending upon what that second factor of m is. Okay, so we've established that that's farther out. And I'm also saying that it's farther out than pi over m1. So if we think about rewriting m as m1 times m2, we can show that this is bigger than pi over m1. So not a lot, but a little bit, enough to allow some aliasing to happen after we do this decimation after the filter. So that's the setup. So that's, again, just kind of some magic formula there, and we'll see that it works, and then you can trust the magic formula. So let's see what happens. So here's after the first filter. Now listen carefully. I'm going to show everything in terms of filter. Technically this shouldn't be z, that should be theta, but I guess I was too lazy to change it. And really, technically, it should be magnitude. So I'm getting a little loose with my labels here, but you get the idea. So I can think of this as the filter, but I can also say, for the purpose of visualization, imagine that the signal going in is just nice and flat over its entire spectrum. So then that spectrum times this gives me the output spectrum. So I can kind of view this as kind of a worst case signal spectrum after the filter. Okay, so that's why I'm going to be showing plots of these frequency responses, even though I labeled them incorrectly. So now after the first decimation, so now view this as a signal spectrum, not as the filter, we know that things get stretched out. So this point gets stretched out to there, and it gets stretched out by a factor of M1. And here I've just done a little bit of algebra and manipulation to show what that point is. And so now we have that, and we can see that that spectrum, again, remember I'm visualizing this as a way to think about where the signal spectrum, after it runs through this filter, the signal spectrum can be all the way out to here before it gets completely, quote unquote, completely attenuated. So that part gets pulled out, stretched out to there. Okay, so aliasing is going to happen. So let's look at that aliasing term, right? We would just take this together with its mirror image and move it up to center at 2 pi. So here is this right here, and now I'm going backwards down that side. And if I know where this is, if that's this far up from 0, this edge is going to be that far down from 2 pi. So I'm just taking 2 pi minus this thing here, and then doing some algebra, and I see that it ends up being pi over M2. And that's the key. This magic formula that I used on the previous slide, well, this thing right here, I picked it because when it gets mapped up and I find this point here, it ends up being pi over M2. So we'll see that the next filter will completely throw away all of this stuff up there. So that is how we eliminate the aliasing. So here's our second filter. We now know that we need to put our stop band of our second filter starting right there, which is just pi over M2. So we're not playing any trick with the second filter. The second filter is, its stop band is kind of right where you would expect it to be, because we need to make sure that it will stop any aliasing that comes from that second filter when we decimate it. So that's why. And this stop band will eliminate that, well, suppress anyway, that aliased replica that we had above. And as we said, we can figure out that, reduce it to that, and say, that's what we need. So after our second decimation, remember this is going to get decimated by M over 2. That's going to get mapped out to pi, stretched out to pi. That's the effect of decimation. Okay, so that's the machinery. Let's talk about the design requirements. So when we design these FIR filters, we're specifying passband edges, stop band edges, and more importantly for this scenario, because those just kind of got nailed down in that little machinery example or illustration or discussion, what's important is the amount of attenuation in the stop band and the amount of ripple that you allow in the pass band. So I don't cover the Parks-McClellan design of FIR filters in this course. I've got some material on that in my Signals and Systems class, so if you need to brush up on that, you can go back. But what you really need to know for this course is the concept that when we specify an FIR filter design, we're saying passband edge, stop band edge, stop band attenuation level, and passband ripple level. Those are the four things that we put into our Parks-McClellan design. So here they are. For a single stage, we would have these two things, and we just saw what those would have to be. And then this is more of a choice as to how good of a quality do you want your signal to be. So obviously, ideally, we would make our passband ripple to be negligible, non-existent, and our stop band level, we'd like that to be all the way down at 0. So these things are in non-dB when we talk about them here. And what about our two-stage scheme? I should have mentioned, let me go back here. Notice that the passband of the second filter, the passband of the first filter, its effective position after the first decimation, it gets stretched out to M1 times theta P. That's why when we design our second filter, again, this should not be a Z there, that's where we put it. Remember I said that the passband stays constant. That's relative to Hertz. So if we take this theta P and map it back to Hertz using the starting sampling rate, it'll end up at some position, FP. And if we take this and map it back to Hertz, but now using the new sampling rate after the first stage, so that would be the original divided by M1, and map that back, it'll map back to the same place. So that's what I mean by the passband stays the same. So basically, the same spectrum of the signal is going through a passband twice, right? It's going through that and it's going through that twice. While I'm here, I might as well talk about the stop band, right? The first stop band needs to be out to there. And so we need to push that down a bunch. But then remember, some stuff gets through and this needs to push that down. So to be sure that everything gets pushed down to the level that we need, both filters have to have the desired stop band attenuation. And so that's what I'm saying here. So the passband is actually split between the two, so that as it accumulates between the two, we'll be sure that we will never exceed a ripple of our desired delta sub P. But each filter must have the desired or the target stop band attenuation. And then these just come from our analysis. That's what we had from our analysis on the previous slides. So we know how to set those. So now we can go ahead and design a filter for this application, and we can design the filter for those two filters for the two-stage application. So let's look at an example. So suppose we have an audio signal, and we're going to fudge a little bit. Normally we like to think of all the way up to 20 kilohertz, but just to make the numbers work out a little nicer here, I'm going to take 18 kilohertz as our upper edge. So that'll be our passband edge in hertz. And suppose it was sampled at 576 kilohertz. And like I said, there could be any number of reasons why we have it sampled that fast. Could be coming out of a sigma delta A to D converter, and the end of that device, it needs to be decimated back down to the regular sampling rate. Or it could be we're implementing some serious nonlinearity to get some distortion effect for a guitar. And as we'll see, we need to upsample by some level. Maybe not 12, but 12 would certainly work. Maybe it's a very serious distortion that creates some pretty strong high frequency harmonics, and we want to keep all those and not have them alias back down. We'll talk about that later. So whatever the reason, this is where we're at. So just for convenience, I've noted that this Fs over 2 would be half of this, so 288 kilohertz. So our goal is to decimate this audio signal that's sampled at this large rate back down to a more reasonable audio rate. So 48 kilohertz is one of several standard sampling rates. 44.1 kilohertz is the most common, but 48 is pretty common as well. It's the sampling rate for digital audio tape. And it turns out that if you look at this and that, that is a decimation of a factor of 12. And if you also look, you'll see that half of that is 24, so that's well above our 18 kilohertz. So we really could decimate a little bit farther, but I just kept things simple here, so we end up with some nice, easy numbers to think about. And also a decimation factor that is nicely factorable into integers. All right, so let's just pick some specs here. These would be application specific, depending upon the fidelity of what you want coming out of your rate change scheme. So I just picked some reasonable ones. Again, these are in non-dB. So that 0.001 and the 0.01, there are rules. If you go back and you look at my notes on Parks-McClellan, you'll see how we convert those into decibels. And this is how we do it right here. So the 0.01 gets added to a 1, and then we do 20 log 10. So that's a up and down of 0.086 dB. So that's just about 0.1 dB. That's a pretty good filter. And then the 0.001 converts into an attenuation of 60 dB. So really good passband, maybe not super great stop band attenuation, but still not too bad. But whatever. We're just trying to illustrate how this all works. So suppose that's our choice. And now we're going to look at what happens for the single stage. So we've got our 18 kilohertz passband edge. Where is that on the theta axis? So remember that theta is our discrete time frequency. I usually use capital omega, but here I'm choosing to use theta because I draw these from Peratt's book where he uses theta. So we convert that into discrete time frequency by taking the frequency divided by Fs over 2 times pi, right? Remember, Fs over 2 maps to pi. So that's our rule, and so we can use that rule to map this to pi over 16. And I technically should say radians per sample here. Okay, so now we've got our theta sub p, that's our passband edge. And remember the stop band edge, we need this one filter in this single stage to create the nth band signal. So that means that our stop band is going to be pi over m, and in this case m is 12, so pi over 12. So there is our passband and stop band edges. And my claim is that's a pretty narrow transition band. And so, as I showed this before, and now I'm showing proper theta versus, a function of theta versus theta. So that's what we're talking about. Fairly sharp transition will lead to a fairly long filter. And so the length of the filter, the reason we care about that is that impacts the number of computations that we have to do for each output sample. So, each output is computed by taking a signal sample times a filter coefficient and then adding them all up. So if the filter has 200 taps, we need to do 200 multiplies and then 199 adds for every output sample. So that's how we measure the computational complexity. Now in MATLAB, there's a command called FIRPMORD, or FIRPMORD. The PM stands for Parks-McClellan. The ORD stands for order. It's a command that will estimate the filter order that you need to achieve the specs that you want. What's inside that? Well, a formula that looks just like this. This was actually developed empirically by one of the big names in DSP, I think back in the late 60s, maybe early 70s, whenever the Parks and McClellan algorithm was coming out. Larry Rabiner published this. And so what's going into this? Well, we've got delta P and delta S. Well, first of all, I should say N here is the order of the filter, and the order is one less than the length. So the order is just the order of the polynomial that corresponds to the filter's transfer function. So we've got delta P and delta S showing up here in the numerator. So as either of those goes up, the length needed goes up as well. And then we see, I'm sorry, that's not necessarily true, right? It's the other way around because there's a negative out in front. So as these go down, N is going to go up. So as we get more stringent on our pass band and stop band requirements, the length is going to go up. So those have an impact. But also, remember, those are just things that we pick to achieve our quality of the output. But this is what is driven by or affected by the switch to a two-stage scheme, right? We talked about how we got transition widths that were wider. So that's the transition width right there. So as the transition width gets narrower, we have some number over the transition width that's going to make the order get larger. So so for our example, for the single stage, we put in our delta P, our delta S, our theta S, and theta P, and it turns out that we get 244. We should round this up, right? So whatever number we get, if it's not an integer, round it up to the next largest integer. And that's the order needed. And then the length is one more. So 245 multiplies every time we apply that filter to compute an output sample of it. So if we use this order estimate, we can get an idea of how many computations we have to do. And we're just going to count multiplies, and we're going to count the multiplies for each output sample after the decimation. So that assumes that we're playing the game of when we're using a filter to do decimation, we just don't compute the ones that are ultimately thrown away. So we talked about that before. So that's why we're doing this after decimation. That means that we'll need L multiplies per output sample, as I alluded to before. And there are M input samples per output sample. So now we're referencing this back to the front end. So it's just one way that we can characterize this. We could reference everything to the output side as well. I'm just choosing to reference everything to the input. You got to compare apples to apples. Due to the decimation, every one output sample, we would have clocked in M input samples for that. So that's how we do that. So if I put all this in, I don't know why PowerPoint did that to me, but did something weird there. It turns out that we end up getting L over M multiplies per input sample. Warning, this L here is the length of the filter, not some upsampling factor. Okay, so I suppose I should have picked a different number or symbol there, but I didn't. So 245 from Rabiner's formula, and our decimation factor of 12 ends up being about 20.4. So for every input sample that goes in, I need to do 20.4 multiplies. Now that might not seem like a lot, but remember, this is not the only thing your processor is doing. And you might be doing this not necessarily on some super fast processor. You might need to do this inside some embedded microprocessor. Let's not say, hey, computing power is irrelevant these days. No, we want to try to make these things as efficient as possible so that we free up our processor to do lots of other things. This is just one simple thing that's going on inside our audio system. So let's continue this and now consider that our 12 is factored into 3 times 4. So we'll say M1 is 3 and M2 is 4. Yeah, and the results would be different if we flipped that around and said the first stage was 4 and the second stage was 3. And I would leave that to you as an exercise to see how that might affect things. And it turns out that order matters. So when you're figuring these things out, you gotta play around with it, or MATLAB will do it for you, but you should know how to do it. So now we're going to specify what our first stage filter needs to be. So remember, we said that pi over 16, that doesn't change. But now here's our magic result that we said for the first stage. Again, for just a two-stage approach, that was our magic formula. And in this case, that ends up being 7 pi over 12. And so you can verify that that's farther out than what we had in the single stage. And then here is our stop band, same as before, and we've taken the pass band and divided it by 2. So instead of 0.01, it's now 0.005. So there's our filter. Again, I've mistakenly put a Z there. Shame on me. And so here's our filter, laid out. It's not really going to be 0 out here, but that's a good way to think about it. So there it is. And then using our diagram from before, we know that this point here will be 2 pi minus this magic number times M1. And if we work that all out, that just ends up being pi over M2, which is pi over 4. So that's the part that matters. So remember, this is the point that our second filter needs to have its stop band. And so that will get rid of the aliasing that is happening from the first stage. So the first stage lets aliasing happen, and then the second stage cleans that up. The analogy I like to think about is, suppose I'm pushing a snow shovel down a driveway. It's okay if a little bit falls off the end and I leave a little bit behind, because I know that on my next pass down the driveway with my snow shovel, I'm going to clean that part up. Okay, so that's kind of the idea. Okay, so there's that figure repeated. I don't think I changed anything. Nope, didn't change anything. And so now we can think about the design of our second filter. So like I said, this point here is where our stop band of our second filter must start. And in general, that's going to be, for this two-stage approach, will be pi over M2. And for our example, that's pi over 4. Now the pass band got moved out. It started at pi over 16, but now after the first decimation, it gets stretched out to 3 pi over 16 because my first decimation is by a factor of 3. But that's the same frequency in hertz as we had before. So we talked about that before. So here's the pass band of my second filter. And here's the specs. Just picking those off from up here. And we know that our pass band is half of our goal and our stop band is at our goal. And so now we, presumably put those specs into the Parks-McClellan design, and we design the filters, and now we could implement it. But we want to check. Our focus here is the complexity of this. So now we're going to go and assess the complexity of each stage, but we have to be careful. We need to compare the complexity on the same measure. So remember, we referenced our computations in the one-stage approach to number of multiplies per input sample. So we're going to have to do the same. We could do both reference to output, but it has to be the complete output of the whole system. So I'll show you how we do that here. So if we plug these numbers into our that Rabiner formula, we get an N1 equal to 11, rounding up if needed, and then going to the length of 12. And just like before, we reference that computation to the input of that stage. So that input that first stage is decimating by M1. So it's going to be L1 divided by M1. So that's 4 multiplies per input sample. I'm not computing the adds, because those usually just track right with the multiplies. Okay, so second stage, we plug our numbers in. Oh, notice that it gets a little bit longer, but neither of those is as long as the original filter. There it was like 245, something like that. Also, keep in mind, we could think about these two filters being convolved together, even though there is a decimation in between. That effective length would be, those two things added -1. So really, the length of the filter effectively are much lower than what we are seeing in the single stage approach. Well, that's an aside. Probably shouldn't have even mentioned that. Maybe I'll edit it out. Okay, so if we plug in our numbers, we get N2 equals 88, bump it up to the length. And now here's the trick. So we need to reference these multiplies. So we would have 89 multiplies per output of the second filter, but we need to take it all the way back to the front of the whole system so that we can compare and just add it to this. This is multiplies per input to the whole two-stage thing. So if this is the number of multiplies per output of the whole thing, now we're going to reference it back. So we divide by M. Well, I should do it the other way. Let me do it this way. We're going to divide by M2 to get it back to the beginning of the second stage, and divide by M1 to get it back to the beginning of the first stage. Now we have 7.4. Those are referenced to the same place. So input and input. And so now we can just add those two things together. So our double stage complexity is now 11.4 multiplies per input. That's about half of what we saw for the single stage complexity. So you might say, oh, 20.4 versus 11.4, that, who cares? Well, remember in this example, that input is coming in really, really, really fast. What did we say? 586 kilosamples per second. So those are coming in fast. And we've got to do 20.4 multiplies in between every one of those input samples. If I can cut that in half, that means my processor can run half as fast, which is good. So now I could reference all of this to the output. So for the single stage, I wouldn't reference it back to the input. And for the two-stage method, I would leave this as 12. And then I'd have to reference that to the output. So I would multiply by M2. And then this would stay as it is. And then I'd compare those. So that's the number of multiplies per output of the whole system. Again, you'd see that it's about half the complexity for the two-stage approach. But remember, those multiplies per output are at the 48 kilosample per second rate. So either way, you get the same assessment. Okay, it's just which way you want to choose as your reference. Okay, so just some comments on that. As I said, left as an exercise, what if you did it in the other order? And I will let you know that, yes, it does matter. And I can't remember which one is better. So I'll leave it up to you to see. And so we went through the details of a two-stage design. You can generalize this to a P-stage design. It gets much more complicated. The order of the choice of these factors really matters. So in principle, you might, you'd have to think about multiple ways of ordering these. I think the MATLAB command that I'll show you in just a minute works all that out and gives you the optimal way of doing that. To be honest, I've not really used that command because I don't do this on a day-to-day basis, but I think that's how it works. And we talked about multi-stage decimation. All the same ideas can be applied for multi-stage interpolation. And so MATLAB has commands for doing each of these. Design multi-stage decimator and design multi-stage interpolator. I don't know what toolbox those are in. Maybe not the signal processing toolbox, maybe something beyond that, like the DSP system toolbox, something like that. So MATLAB has those commands, but doesn't necessarily have them in the raw MATLAB or even necessarily in the signal processing toolbox. Okay, so you can go check those out. I'm not going to go into any more detail on those. We got 2 slides left, and there I want to talk about another form of multi-stage approach. I alluded to this in the previous note set, the fact that we can interpolate by L and then decimate by M to get a rate change of L over M. And you almost always want to go up first and then down because, if this is our target and we went down by M first, so much aliasing will happen, we'll never recover it. So you always want to make sure that at every point in your system, you never take your rate down lower than your final target rate. That's kind of a good rule of thumb. So for just a 2-stage rational factor viewpoint here, we always want to do the L first and then the M. So sometimes these L's and M's get pretty big to create just the right rational factor, right? So the rational factor might not be that large, but to get it, we need a big L and a big M. We'll see an example in just a little bit. Now, notice that we interpolate followed by a filter to get rid of the image spectra, and then we filter followed by decimation. Here's our discrete time, essentially anti-aliasing filter to create an nth band signal there and eliminate any aliasing that would happen if we didn't have that there. Well, a cascade of 2 filters together can be replaced by a single filter. So you could design these 2 separately and then just convolve their impulse responses to find out what this composite is. Or you could think about this system as a whole and design that to be what you need. And again, I'm sure MATLAB in some toolbox or other has the design for this kind of thing. So I didn't look up the command for that. But it will implement this if you just tell it L and M here and shove a signal in. It has some default filters that it will apply. And so it will resample the input X at a rate of L over M times the original sampling rate. And it applies some FIR low-pass filter. There's a default method that it uses to figure those out. I think it just does it in a single stage. And then here's a cool thing, right? We know that filters cause delay. So comparing this to this can sometimes be a challenge because there's going to be a delay between them. But this command compensates for that delay introduced by the filter so that you can nicely compare them. So it's nice for offline processing. That's the only way you could really do this compensation. Offline computation to kind of see how well your design is working and compare the output to the input. And that's a nice little exercise to do. So now how to actually do this kind of thing efficiently. Like I said, I don't really know how efficiently MATLAB does this in the resample command. I think it just does it inherently in a single stage, but we've just seen multiple stage ideas turn out to be helpful. So let's see how we might do a rational change using a cascade of rational changes. So the example here is converting something that is on digital audio tape, which has a sampling rate of 48 kilohertz, to compact disc form, which has a sampling rate of 44.1 kilohertz. So suppose you recorded something a while ago, back when digital audio tape was more popular, and now you want to put it in a CD kind of format. Same sampling rate, by the way, that's used in MP3s and WAV files and things like that for typical audio application. Okay, so let's look at this. Let's look at the ratio of these. So we take 44,100 divided by 48,000, cancel off some zeros. There's our rational rate change. But, let's look for some common factors. So there's a common factor of 3 between those. And so we end up with 147 over 160. And I don't think that can be further factored into two smaller integers to form that rational relationship. Okay, so once we cancel out this common factor, we end up with our L and our M, and those are big numbers. That L is big, the M is big, and so we've already seen if we want to design a filter to upsample by 147 and then downsample by 160, the implementation of it is not going to be very efficient. So we just looked at a two-stage example for decimation only. So the single stage approach is inefficient. And we can also see that just from the fact that look how high the sampling rate is. So this filter has to operate with samples coming in that fast. So one sample every 1 over 7 times 10 to the 6th, something like that. So that's pretty fast, given that we really are going to end up with samples at 44.1. So we kind of want to avoid that. So it's not just the number of computations that you have to do, it's the rate at which you have to do those computations. So let's look at a multi-stage approach. And so here I've factored 147. Thankfully, it's not prime. Otherwise, I'd be in trouble. And so, maybe this was a choice 44.1. 48 kilohertz was in existence, I think, when this was chosen. And so maybe that was chosen to allow a rational change between those with non-prime factors. So anyway, we factor this out and we factor this out. A couple things to note here. This could be factored further. I didn't do that. I just factored it into 3 factors, and we could factor each of those out even farther. So the 8 can go down into 2 times 2 times 2, and the 4 can go into 2 times 2. I don't know if there's a benefit to doing that, but these numbers are all less than 10. So this might be okay. I'm not saying this is the best way to do it, but it is a viable way to do it. And now if we go through this, we can see, I don't actually track this, but you could track through to see what the sampling rates are at each position. So how fast does this filter need to work? Well, we go up by 7. So it's 48, goes up by 7. That's still pretty fast, but not anything at all like up by 147 to that fast. And I will also say that I've mixed and matched, right? I took the 7 and the 5, the 7 and the 8, and the 3 and the 4. But there's lots of other ways that I can mix and match these, right? So I could mix 7 and 8 and 7 and 5 and 3 and 4. In fact, there's, I think, if you discount things that would drop us down to a rate lower than our goal of 44.1, I think there's like maybe 18 ways of organizing this, and not all are going to be as good as others. So you want to pick those so that you get the best efficiency, and also likely that would hinge on making sure that the intermediate sampling rate anywhere in the system, first of all, never drops below 44.1, but then the largest sampling rate that you'd have anywhere, you'd want to pick the order to make that largest internal sampling rate the smallest of all possible choices. And then finally, there are ways that this operation can be implemented using polyphase. And Peratt's book goes into how to do this rational change with a polyphase structure. Again, beyond the scope of this course, but if you're interested, there's lots of places out there to look at. So multi-rate signal processing is a huge area. We've only very barely scratched the surface of it, but if you want to dig into this for whatever you need it for, lots of good books out there for that.